And I got the chance to work with two wonderful students for the ERP, Hüsnanur here and Hasan here. And we all looked at parts of Egner's book on Markov numbers and 100 years of uniqueness conjecture. Markov numbers are really exciting. They are connected to cluster algebras and rational approximations, and there's some very cool combinatorics involved. And there's to talk some about that cool combinatorics. About Markov numbers, and today I will talk about combinatorics of Markov numbers. This Diophantine equation is called the Markov equation, and we will try to find some solution and understand the solutions. We call solution triples with solution triples, which is most integers, are Markov triples. Maybe right now you can try find some of them, and if you want, share with us.
0, 0, 0.
I said positive integers.
Oh, sorry. 1, 1.
Yeah, 1, 1.
1 minus 1 minus 1. As I think. Oh, it's cool.
Yeah.
Nine. 169.
Let's solve this calculation. We can find 1, 1, 1, 1, 1, and then just say 1, 2, 5, 2. By the way, we called numbers in solution triples Markov numbers. At first glance, finding solution triples for this equation, it seems easy, but after a few solution triples, it's not easy. So, find more solution triples. We have a green insider. We'll use the solution triples that we already found for finding some solution triples. Let's suppose we find a solution triple M1, M2, and M3, and we know this number satisfies the equation. And if we set M1 as the x, we get a quadratic equation like that. And we know that M1 is one of the roots of the equation, and there is another root of the equation because the equation is quadratic. Let's call this other root M1 prime. You know that M1 prime satisfies two conditions, and M1 prime, M2, and M3 is a solution triple too. But is this solution triple Markov triple too? What do you think about that? I mean, is M1 prime is M1 prime positive integer? Why?
Yes, because for example, you said M1 prime times M1 is equal to is sum of squared. So
3 and 2 and 3 minus and 1. M1 prime is 3, M2, M3 minus M1. M1 is positive, M2 and M3. Subtraction.
Have another.
Ah, yeah, that one is positive.
And next solution triple. So we can apply same thing for 1 and 2 and 3, and apply the algorithm for these numbers. We can get at most 3 in the solution, and with half of the solutions we can construct a graph. Let's start a solution that we already found, 1, 1, 1. Apply this algorithm for 1, 1, 1, we get 1, 1, 2. If we apply the algorithm for 1, 1, 2, we get 1, 1, 1 and 1, 2, 5. And if we apply the algorithm for 1, 2, 5, we get 3 and 3 new solutions. With this new solution, we can construct a binary tree that we called the Markov tree. So, let's examine the maximums. You can observe the maximums in this tree are increasing along the tree. And if we apply this algorithm for the numbers which are non-maximal in the triple, we get two other triple with larger maximum. If we apply this algorithm for maximum number of the triple, we get a triple with smaller maximum. This is the consequences of our quadratic formula. Suppose that M1 is greater than M2, M2 is greater than M3. If this, and then sliding M2 into our quadratic equation, we get something like that, and this is smaller than 0. If we, as looking at the graph of our quadratic equation, then you see that if M2 is negative, then M2 implies between M1 and M1 prime. So that's M2 is bigger than M1 prime. Like we observed, the maximum gives us nature a bit smaller maximum. And if we do the same thing for M2 and M3, again we can conclude that can have another triple with larger maximum. We code triples with repeat numbers, singular triples, and others non-singular triples. For example, 1, 1, 1 is a singular triple. And the word says that 1, 1, 1 and 1, 1, 2 are the only triples with repeated numbers. That is beautiful because if triples have repeated numbers, then we can get three new solution, but they are non-singular. Always we get three other solution, and this tree goes to infinity. Let's take a Markov triple, and if we apply this algorithm for this triple to get smaller maximum, at the end of the process, we reach 1, 1, 2, and then 1, 1, 1. Means start with non-singular triples. The end will be singular triple. So we can conclude that theorem says all the Markov triples on the Markov tree. So with help of the Markov tree, we can find all the solution triples. And apply the algorithm again for the Markov triple. We know that every new triple have a min maximum in number, and number appears as the maximum of this triple. So we can say that every Markov number appears as the maximum triple. But are these Markov numbers appears exactly once as a maximum in a Markov triple? That's the question Frobenius asked 1930. The Uniqueness Conjecture, which is unsolved for 100 years, says every Markov number appears exactly once as the maximum in a Markov triple. Now let's change. We have some equations of generalized Markov equations, which is very similar to Markov equation. For example, this equation can be an example. We can do the same thing for the equation too. We can create a quadratic formula and can find the solutions with help of this formula, and then we can say that the only singular triples are 1, 1, 1 and 1, 1, 3, and then we can say that all the solution triples appears in the tree. So we can do the same things for this equation too. And for more information about this equation, can read the article by Yasuke Gyoda at 22. And now we'll examine the combinatorial relation between Markov numbers and domino graphs. But the first defining domino graphs, we have to define snake graphs. So let's take a rational number p over q between 2 and 1, and p and q are relatively prime. For example, let's take 3 over 5. And then we draw a 3 by 5 rectangle. Then we draw a diagonal. And this diagonal is an intermediate let's point of an intermediate let's point. Can you see the reason? We take two numbers which are relatively prime. And there is no divisor, so this diagonal does not hit any intermediate let's points. And then we'll try to find closer paths to our diagonal. There will be two paths below the diagonal and above the diagonal, and these paths are symmetric. And the squares between paths called snake graphs. Snake graphs and their matchings are important objects in algebra and their combinatorics. And the domino graphs are the snake graphs which we stretch every row k squared to k minus 1 and add one extra square each column. for 2/5, we have a domino graph like this. We try to calculate perfect matchings of domino graphs, but at first I have to say why I speak of domino graphs, because you can cover them with dominoes, and the coloring of domino graph of 3/5 is like that. And what is perfect matching? A perfect matching of the graph is a set of vertices over all the vertices. For example, for 1/2, we have a domino graph like that. For domino graph, for this domino graph, we can we have 5 different perfect matchings like that. So the matching number of this domino graph is 5. Let's try to count perfect matchings of this domino graph. We have a special recursive algorithm for this. For the first square, one square. First square, we have 2 different perfect matches. For the first 2 square, we have 3 different perfect matches. We apply our recursive algorithm, which says if next square in the same row or column adds matching numbers of what's 2 squares. For example, for the first square, we have 3 plus 2, like we calculated. And if there's a chain, at the matching numbers, at the matching number of last square and third last. I mean, for the fourth square, we have 5 plus. And this way we can recursively calculate the perfect matching number of domino graph, and this gives us 433. And the important result is 433 is a Markov number. So matching number of domino graph gives us a Markov number. Can we say the same thing for all rational numbers between 0 and 1? The term says us for all rational numbers between 0 and 1, matching number of domino graph of rational numbers is a Markov number. So you can get all Markov numbers right away. And we have a special relation. We have a surjective mapping between rational numbers and Markov numbers. Now we have a new variant of the uniqueness conjecture, which says all the domino graphs have distinct matching numbers. Then, if all the domino graphs have distinct matching numbers, mapping for all the rational numbers, there is a correspondence correspondence of distinct Markov numbers. And different ones, mapping is a conjunction too. So, projection. So, we conclude new variants of uniqueness conjecture. And the end of my presentation is my reference, and thank you for listening and attention.
Thank you for the presentation.